Uh, I guess on the same topic, what does one hot mean?
So one hot is just the same as, that only one of those outputs can be active at a time. So that's all one hot means. It just means one of them is hot, one of them is high, one of them is active, one of them is asserted. All those things mean exactly the same thing.
Okay, gotcha.
Okay, so we'll get started here, but before we pick up where we left off, I want to talk about the next lab. So the next lab is very important. The first lab was kind of a introduction, get to know the simulator a little bit. But the next lab that we're going to do is going to be the foundation of the rest of the labs that we'll do for the rest of the quarter. So next lab, this is, foundation. That means a couple of things from the point of view of the student. I know how students think. The important thing about this is that, and I put this in the notes, do not plagiarize this lab. There's two reasons for that. There's the reason that you'll appreciate is that if you do, you're going to get a 0. And then there's the reason I'm going to appreciate, which is because I want you to really understand this lab and what's going on, because if you don't, it's going to make the rest of the labs really, really difficult. So you want to spend some time on this next lab and understand what's going on, how it works. And again, do not plagiarize this first lab. It will be very, very detrimental to your learning and your grade. All right, having said that, let's move on. Okay, so very briefly, we'll just mention what a basic block is, because compilers go through your program and find the basic blocks, and they use basic blocks as as their chunk of code that they look at for how to do optimization. And again, compiler optimization used to be hugely important, and a huge amount of research was done on it, but it's sort of done at this point. So it's important to just understand this term, but many of you will never ever see it again. And here we won't spend much time here either, because in the modern versions of MIPS, RISC-V, and ARM, they all allow and assume, whoops, oh, darn it. Gosh, I'm so sick of that happening. They all assume that you can do any branch. Recall that in the code that we've looked at so far, we've used two different kinds of branches: branch on equal and branch on not equal. And it turns out that neither of those branches actually requires you to do a subtract. I mean, you think of it as doing a subtraction because you check to see whether the values are equal. And the way the general way of seeing if two values are equal, or you subtract them and you see if the result is 0. But if all you're trying to do is check to see whether they're equal or not, you don't really have to subtract them. You can just compare them bit by bit and see whether any of the bits are different. And you don't need to do an actual addition or a subtraction to do that. But in any case, in all of the three modern versions of the MIPS, RISC-V, and ARM architectures, they allow you to do any of the branches, like greater than, or less than, or equal to. All these other branch types are also single cycle instructions. Unlike in the original in the original version of the MIPS architecture, for speed purposes, they would turn any of these fancy branches that actually requires a subtract, because as soon as you're not just checking for equality, you have to actually do the subtraction. And so all of those would be turned into this SLT, which is the subtraction. That's actually doing the subtraction. And then after you do the subtraction, then you would just do the standard use of either BEQ or B branch on not equal. For our purposes, we will just completely ignore this whole thing, and you can use any branch you want. Any of the branch types are perfectly available to you, and you shouldn't think about it any more than that. You just pretend like any branch type is available to you. Don't worry that it's 1 or 2 instructions. The compiler will do all that work for you. And again, as we said, the reason that you don't do these fancy instructions in hardware in the original architecture is because they require a subtract, and that would slow the whole thing down. But again, the modern architecture has solved this in a different way. So we're not going to, we won't, this is not a history course, so we don't care about it. Again, we're going to come back to the whole stuff of the 2's complement number system, so we don't care about this right now. We'll come back to this. Here's our main focus for tonight. So what we said so far is that basically the processor only has the ability to do 3 things. So just to summarize here, we can do ALU operations like add. So, whenever I say ALU, you can just think add. So that's one of them. The second is load store. And the third is branch. So don't forget that. So that's our fundamental operations that we can do. And then we said, out of those, basically we have 2 programming constructs basically, and there's really almost only one, but we're going to pretend like there's 2. There's loops, and then there's if then else. If then else. And so that's our 2 programming constructs that we can construct in any program out of. Any and every program is just built out of these 3 operations and these 3 collections of operations, if you will, that do all of the things that a program can do. And of course, the 0th one here is just, doing, again, just adds operations, whatever you wanted to actually do to the numbers. Of course, that's the 0th, programming paradigm. That's the obvious one, the null one, if you will, from a software parlance. Okay, now, in order to make your program neater, we include the ability to do procedure calls. And in various languages, these are called procedures, methods, functions. I don't know, almost every language that they invent a different name for this. But it's all the same thing. It's where you give something a name, and we'll use the classic one. The classic is square root. So you have a function called square root. For example, there's many other ones. We looked at another one that a couple times already, called swap. That was a routine that you call. So you call swap, you call square root. So all of these things are all these procedures, methods, functions. The first thing you do when you want to use them is you call them. And you call them with a set of parameters. And again, for square root, there's one parameter. There's one thing that you pass to the square root function. It's the thing that you want the square root of. So very simple. And so we have a special couple of registers that we can pass parameters in. And so you put the value that you want the square root of in that register. We'll see that in a moment. And then you call the procedure, transfer control equals call. And then if necessary, you generate space in order to do the procedure. Often that's not necessary. Hopefully you can do it all in the registers. But if you can't, you're going to have to generate space in the registers. If there's too much to do, square root is simple enough that you can do it without acquiring more storage. Then you do it, you calculate the square root, 10 dozen instructions or so. We will look at exactly how to calculate a square root in a couple of weeks. Fascinating. It's a great magic trick. And then when you're all done, we'll put the register in, we'll put the result in a specific register, just like we put the parameters in specific registers. We'll put the result in a specific register, and then you go back. And so this is pretty straightforward. And the reason, of course, that we want to do this again is that you may use square root in your program many times. You may have it in a loop, and you don't want to put the 20 instructions that it takes to compute square root in that loop, because you use it over and over and over again. So you want to put it off in a library, a set of library routines that are called all the time, because you don't want that 20 instructions to appear in your program, 10,000 times, or how many times you use it. That wastes space and makes your program ugly. Because in your program, when you write it, if you say square root, it's very obvious to the person reading your program what it is you're doing. If you just put a whole bunch of code there, it's not nearly as obvious. And of course, again, you don't want to do that just because it wastes a huge amount of space. You have to put those instructions in memory every time you do it that way. If you don't make a procedure and then call it when you need it. Okay, so the reasons then that we want to use procedures are for reuse, reusability, and for readability. So those are the two reasons we want to use procedures. We want to reuse the same code over and over again, and we want to make it easy to read your program, or easier to read your program. We want to make the important part of your program as short and as readable as possible. Okay. All right, so here's the register usage for a procedure call. As we said, we have specific registers. We call them A for A equals argument. The arguments of the procedure or the function or whatever you want to call it. Here's where we'll put the results. The values, I think it stands for whatever. Anyway, that's where the results go. And then here we have the first time where we figure out why we have some S registers and some T registers. The reason is because of how procedures use them. So the caller calls the procedure. The callee is the guy who is called. That is the procedure. So in the procedure itself, the square root code, if you will, the square root code can use any of these registers, and it can just write over them without worrying about saving the values that were in there before. So when you call a procedure, if you have anything in T0 through T9, you have to assume that when it comes back from the procedure, that those values have been lost. You can't assume that anything that was in T0 through T9 is still there. S0 through S7, the procedure is not allowed to harm the value in those registers. When you return from the procedure call, when you return from the square root, whatever was in these saved registers when you called it must still be there when it returns. So if it uses any of these registers, it first has to save them. And then when it's done using them, it has to then restore them. So must be saved and restored by the callee. So of course, the best thing for the callee to do is not use those registers, but that may not be possible. If it's a really complicated routine, he may need all of the registers to do it. We don't care about this. We'll just ignore this, and we'll just ignore this. We care about this one. That's the stack pointer. And we care about it because the stack is where you're going to save things if you have to. If you have to save something, one of these S registers, you're going to put it on the stack. And the stack is in memory. It has to be, because there's no other place to save anything. All you have is the registers and the memory. And so the stack is a stack. It works like a stack. Hopefully everybody knows what a stack is. It's a thing that you push and pop off of. So when you push something on a stack, it increments the stack pointer. Put something else on it, increments the stack pointer again. And then when you pop things off a stack, it gets the value back and pops the stack pointer back. So, so a stack gets bigger and gets smaller as you push and pop things on and off of it. Hopefully that is not a new concept. Okay, and then finally, this return address register is important to us because this is where, when we call a routine, when we call a procedure, we have to know how to get back. We have to know where to go back to. So this is where we put the return address. And let's just draw a little piece of code here, or just abstraction of a code that's to say what we're talking about here. So if our program, here's the main portion of our program, and it's executing along. What happens when we call a subroutine is that, we go off to the side here and we execute some other instructions, and then we come back to where we were, and then we go on. So the loop of execution here looks like this, right? That's what a procedure call looks like. And this here is the square root code, which is stored off somewhere, and everybody knows where it is. It's in the library routines, and anybody who wants to use it can call it. So recall that the way we execute a program is that, you know, we have this thing called the PC, the program counter. And the program counter just increments along one instruction at a time until we have some sort of branch. And so from our perspective, a procedure call is just a very fancy branch. Because what we're going to do is we're going to, instead of executing straight through here, right? When we get here, we're going to go over to here. We're going to branch over to here. And the only thing that's really fancy about this branch is that when we get to here, we've got to go back to where we were. And so the fancy thing about a procedure call is it's a branch with a thing called a side effect. And the side effect is that PC plus one, the program counter plus one more instruction, gets put into register 31, the so-called RA meaning, you know, return address, the return address. And of course, the question immediately is, well, why PC one plus one? Well, that's obvious because at PC is the call. That's the call instruction. And by the way, the call instruction is called jump and link, JAL. And this is the link back to where we came from. So that's why it's called jump and link, because it branches over here or jumps over there, if you will. And then when it gets here, it has to return. And so the way it returns is it wants to return to the next instruction after the call. And so that's why it puts PC plus one into the return address. And so when you get here to the end, the last instruction of every procedure is a jump register RA. And so what JRRA does is it just puts RA into the program counter, which takes you to here. So how's that? Is that pretty clear? Oh, sorry, go ahead. It was a question.
Before we move on to the next slide, why are there separate registers for arguments into a function and results out of a function? Why couldn't you use the same registers for both?
Well, you can, clearly. This is by convention. This is so that someone can write, this is so that, you know, you can write a program and somebody else can have written the library routine. And by convention, we agree that okay, the arguments are going to come in on these registers. I'm going to put the return value into these registers. And then there's the set of registers that I can trash if I'm the square root routine if I want, and there's a set of registers that I can't trash. These are just things that software people have agreed upon.
Yeah. But if I'm designing a processor and I'm setting these conventions, if I'm telling people, you know, if I'm designing a processor and I'm saying I have these two registers dedicated for result and these four registers dedicated for argument, while I'm designing the processor, why wouldn't I make the convention to use the same registers for both? So I have, you know, more registers available for general use.
Because the software folks told us what they wanted us to do. They said, do it this way. And this is what we did. Right.
All right.
So from the processor's point of view, right, it can't tell any of this, the processor, right? The only thing that the processor can tell in all of this is this, because by definition, when you do a JAL instruction, it puts PC plus one into this register. So from a hardware perspective, we picked one register to put that. and we pick register 31. Why not? It doesn't matter which one you pick, but we just pick the last one. The processor, right? It doesn't know any of this, right? These are software conventions, right? So when you say the processor design, the processor design does not enforce any of these things. Okay. This is not there's nothing in the design of the processor that knows about any of this. From the processor's point of view, there's just there's 30 instructions that are all 30 registers that are all the same, and then this one here that's different. And that's not quite true, because remember, register 0 always is hardwired to 0. So that the processor knows that. It knows that that register 0 is hardwired to 0, and it knows to put the program counter +1 into RA. All the rest of the registers are completely generic, and you could not do this assignment. You could make this assignment to any other set of registers rather than 4 through 7. Again, none of this is in hardware. Is that clear? This is just an agreement amongst software people of how to use the registers. Is that okay? Does that make you happier?
I have a quick question. So what is the difference between JRRA and PC+1?
Well, JR is an instruction. This is the last instruction at the end of the square root routine, or at the end of any procedure, will be JR, which stands for jump register, using the register RA. Right? And so jump register always will take whatever register you pointed at and put it into the program counter. That's what jump register means. It means take this register and jam it into the program counter. And at the end of any procedure, you're going to pick the register RA, because that's where, when you did the JAL, that's where it put the program counter +1 into RA. That's the side effect of JAL, right? It has that so-called side effect, an important concept in processor design. So JAL has the side effect of putting program counter +1, that value, whatever it is, into the register RA. Is that clear?
Yes, thank you.
Any other questions about this?
One question. So
Yep.
for RA, do we set RA to PC+1 before we jump, or is it already set to PC+1?
No, it's a side effect of the instruction JAL. You don't do anything.
Oh, okay. So
You
once
can't.
target.
Yeah, you have no ability to do that. You just execute the JAL, jump and link, to a label, right? So in your code, you're just going to say all you're going to see is JAL square root. That's what the instruction that you write will look like.
Gotcha. And then it does the PC+1.
And auto-magically, it's going to put program counter +1 into RA. And then when you get to the end of square root, you're just going to do JRRA.
Gotcha. That's neat. All right. Thanks.
Yeah. So this concept of using procedures is so important that these little features of the hardware are there to make this work.
Another question. How does the callee know if we have to save the save registers, or does it know? Or should we just always save the registers no matter what?
Well, the callee only has to save the registers S0 through S7 if it uses them. If it doesn't use them, then it doesn't need to save them. right? Because if it doesn't use them, you know, they'll, whatever was in them, you know, when it got called will still be there when it goes back.
Okay, so before doing a load, you would always do a store for that particular S register.
If you use any of the S registers, you're going to see that you must first put it on the stack. We're going to look at that in 1 second here. As soon as we get off this slide, we'll see it. You will see exactly what it is you have to do. So let's just move on, and we'll come back to that if we have to. So here it is again. The instruction that you execute is JAL to procedure label, and again, I've just been using the example. So for example, square root. So JAL square root is what you would write. And I said, you know, the address of the following instruction is put in RA, and the address of the following instruction is program counter +1, because you're currently at program counter. And then again, at the end, you're going to put JRRA, which jams RA back into the program counter. Blah, blah, blah. Don't worry about that. It's true, but that's just confusing for right now. Okay, so here is a so-called leaf procedure. Now, what the heck does that mean? Well, so remember when I wrote that little piece of code there that I said, here's the main, and then we're going to go off and do the procedure and come back. And so as drawn, this is a quote leaf procedure. But if inside it, I say, oh, I'm going to call another subroutine from inside this, and it's going to do the same thing and come back inside that procedure. Now this is not a leaf, and leaf here is, you know, the word leaf like on a tree, right? The leaf is the final thing out there. There's nothing after the leaves. So this is now not a leaf, and now this one as drawn is a leaf procedure. Okay, because we haven't shown any call going out of it. So it's a leaf. So a leaf procedure is one that does not itself call another procedure. Okay. All right, so here we are. We have this you know, piece of code here, and inside it we're going to do our famous boring computation. We're going to compute this value of f, and we're going to return f. And the arguments, you know, this just says that they're integer, right? You know, we now all are experts at C. So we have 4 integer arguments, and that's the ones we're combining together here. And we're going to pass those arguments. Conveniently, there's 4 of them here in our 4 argument registers A0 through A3, because that's what they're there for. And then note that we're going to do something really stupid just because we want to illustrate what happens. We're going to compute F0 into S0. And since we're going to trash S0 because we're going to do the function and produce the result in S0, since we're going to trash S0, we're going to have to save it first on the stack. And then he doesn't note here, but we're going to have to restore it when we're done. Just saving it doesn't do any good. We have to save it and then restore it. So, and restore. And the result, finally, we're going to take it from S0 and we're ultimately going to put it into V0. And of course, you're going to ask the question, well, why didn't you just compute it into V0 in the first place? Which is, yeah, what you should do. But again, we want to illustrate how to put something on and off the stack. So we're going to do it this dumb way. Okay. So here we go. So the first thing you see here, since he knows he's going to trash S0, is that he adds a -4 to the stack pointer. SP again is the stack pointer. So the first thing then to note about the stack pointer is that if this is all of memory, the way memory is organized is that down here is the OS. And then here's the code. This is the way memory is always organized. And then here's the data. And then up at the top is the stack. And the stack grows down and data grows up. And hopefully they never hit each other. If they do, the program's probably going to crash. So data gets bigger because of dynamic objects. And the stack can get bigger because you push things onto it. And often if you have a memory leak, what happens is that the stack keeps growing or the data keeps growing, right? If you have any sort of program error, that's what can cause these two things to ultimately hit each other. Now, modern programming languages, this almost never happens because they have such incredibly good checking in them to make sure that you don't screw up. But in the old days, you know, this would happen all the time, and you'd spend a lot of time trying to figure out what was wrong with your program. Anyway, so here we go. So we add -4. And again, so why is it -4? Well, it's -4 because the stack grows down. So that's why we have to add -4, because the stack is growing down towards the data. And then we do a store word of the value we want to save, which is S0, and we put it right there at the stack pointer. So that's a push, right? So that's push on stack. We'll use software guy's point of view. And then we do that same old stupid computation, 2 adds and a subtract. And we note that the final subtract, we did it into S0. And then we move the value into V0. And again, you say, why in God's name did you do that? Well, again, just for illustration purposes, right? We wanted to trash S0 so that we saw how to save and restore it. So then when we're all done, when we're done with S0 and we put the value, the result of the function into V0, then we have to do a load word from the stack pointer and put it back into S0. And so this is the pop stack. So push, pop, save, restore. And then there's our put the stack pointer back. So this is again, so we don't, so that a stack otherwise will grow unbounded, right? So when you pop something off of it, you have to put the stack pointer back. So now we add 4 to it. So here we added -4 and here we added 4. So clearly when we're all done, the stack pointer is going to be the same value as when we started this whole thing, because 4 plus -4 is 0. And then we do the JRRA. And remember, magically, RA has PC plus 1 in it. Because when we called this thing, when we first called it with the JAL, that put PC plus 1, that is the address, the instruction address of the next instruction after the call, it puts it into RA. That is again, the side effect of that instruction. Okay? Is this good? Everyone happy with this piece of code?
I don't understand the denied at V0 S0, and why is it 0 at the end?
Well, because this is just a move. Again, you know, a good programmer right here would have just said move, right? V0, comma S0, right? Move S0 to V0, right? Because then it would have been absolutely clear what you're doing here. But this instruction doesn't exist, the move instruction, but it exists only as a pseudo instruction. So if you write this, what you get is this. Because if you add 0, this is register 0. If you add 0 to S0 and put it in V0, that's the same as just moving S0 to V0, right? I mean, you can add 0 to something, you know, all day long and it doesn't change it, right? So this is S0 plus 0. So this is S0 plus 0 going into V0. that clear?
Kind of like how the fastest way on x86 to set a register to 0 is XOR EAX EAX.
Yeah, because they don't have a hardwired 0. The beauty of these modern RISC architectures is they have enough registers that they can just dedicate one to the value 0. x86 has so few registers because of its historical, beginnings that it doesn't have a 0 register.
Can we use the number 0 instead of the ZRO?
If you put $0 there, it will do the same thing.
Oh, okay.
Again, it'll turn it into accessing register 0 pretty much no matter what you put there.
Yeah, so we could use a add immediate there with a actual
You can,
literal 0.
yep, you can even use add immediate with a 0. That'll work too. There's so many ways to do it. Yeah, that's the least important part of this piece of code. Sad that we're discussing it. All right, so here is the tricky part. This is where you got to be very, very careful. So let's generate just a little bit more space here. Thank you. So here's our main. Procedure call that we did. So here was PC and here was PC plus 1. So this one works just fine. No additional thought required. But as soon as we do this, we have to be very, very careful. And the reason is because when we did this JAL here, we put PC plus 1 into RA. And when we get here, we expect we expect PC plus 1 to be in RA so that we go back to there. Sadly, when we do this JAL here, it's going to put PC plus 1 prime, let's call it. That's a different value. PC plus, it's some other PC plus 1. It's going to put that into RA. PC plus 1 prime into RA. And that's because when we get to here and do the JRRA, we need PC plus 1 prime in RA so that we come back to here. But now we're in trouble because as we then continue on, when we get to here, what's in RA now is PC plus 1 prime. So if we come to here and we do JRRA, we're not going to go to here. We're going to go back to here. And now we're in an infinite loop. And this will happen all the time to you if you're not careful. So if you are not a leaf procedure, then you must save RA on the stack. Okay, if you are not, this is not a leaf, and this is a leaf. So if you are not a leaf procedure, you have to put RA on the stack and then you have to get it back. You have to put RA on the stack before you do this JAL. And then before you do this JRRA, you have to get it back off the stack. So let's see that happen.
Is that just an optimization in the case of leaf nodes? Because every other CPU architecture I've ever seen, 6502, x86, all of them do that for you.
Do what?
Push and pop the return address from the stack.
Well, you mean there are push and pop instructions, you mean?
No, I mean when you say return from a function, it will pop the return address off the stack, and then return to that, not jump to whatever's in some random register.
Yes. So in all those other architectures you mentioned, those are all CISC architectures, right? So they are not load store architectures, right? They are. So
That's true.
We have CISC and we have RISC, right? We have reduced instruction set and we have complicated instruction set. And remember what we said before is that all those processors you talked about, those were all from the era where, hey, we're going to make the instructions complicated, because what our view of the world of how a computer should be built is that the instruction should be as close as possible to the high level language type of instructions. And sadly, high level languages got to be more and more complicated, and that got to be harder and harder to do. And so those instruction sets became more and more complicated. And as a result of that, those processors just became slower and slower and slower with every generation. And so that's where RISC came from. It said, hey, this is really stupid, right? What we really need is something that can just execute just the basics as fast as possible, and then let software do all that. So when you say, you have to do this, well, once you leave this class, you will never do this again unless you happen to be writing assembly language code, because the compiler is going to do all this for you. But the reason we're here is because we're trying to figure out two things. How do you build the fastest possible processor? And then what does the compiler have to do in order to make that, all transparent to you? Because all of this that we're talking about is going to be completely transparent to you when you're writing in Python or Java or C or C++ or Scala or any other high-level language. You won't see any of this, right?
Hypothetically, hypothetically, if you put like a jump to a different instruction, like right after you branch off to the other method, and then at the end of that method you jump back, would that work?
Say that one more time.
Let me find say one line of code is the instruction to go off to the method.
So that's JAL.
Yeah. And then the next line of code right after that is
JRRA.
Or how when we're doing a loop, we have an instruction that just says exit and that's it?
Well, exit is not an instruction. Exit is a label.
Well, a label, yeah. If you put a label in the line after the JAL and then jump to that label at the end of the method, would that work?
Yeah, sure.
Cool.
Yep, it will definitely work, right? I mean, it will no longer, this piece of code that you were trying to have be, reusable is no longer reusable in any way, right? It's now completely custom.
Gotcha. Yeah.
Right. You're negating the whole concept, right, by doing that.
Yeah.
But it's a good question, and the answer is yes. But you see what happens as soon as you do this piece of code becomes custom to your program.
Gotcha. That makes sense. Okay. Thank you.
So it's, yeah, it's worthless now to anyone else. So you've lost the reusability part. The readability part will still be there because, you know, you put that routine off somewhere, right? And so if it's a routine that, you know, nobody else ever wants to use and you're just using it in your program, that'll work. But of course, if you want it to go back to if you want to use it more than once, it won't work either, right? Because you can only have one label of, you know, of that value in your program. So if you try to call it somewhere else, it won't work. So you see, this is a really magical trick here to do this, right? To get that thing, you know, that got stored away auto-magically and then be able to use it to get back, right? That's absolutely critical to the function of what we're trying to do here. Okay, so as we just said, before you call another procedure, right, you got to put RA on the stack. And then anything else that you may need after the thing comes back, you have to save as well. But you know, we already said that. That's the same. And then you restore when you're done. So the author says, okay, you know, that's too simple. Let's make something really, really complicated here. And anytime in computer science you want to make something really complicated, all you do is you just make it recursive, which is what he does. Is he gives us a piece of code here that's a you know, a non-leaf procedure called fact, which is short for factorial. This is computing the factorial, remember, which is, you know, factorial of 6 is 6 times 5 times 4 times 3, blah, blah, blah. Anyway, he computes it recursively. So this routine fact calls fact. And, and so you get this incredibly complicated piece of code here, which, you know, we're not going to spend any time on. The important pieces of this code is that since it's a non-leaf routine, the thing we just want to note is that he puts RA onto the stack. And then because of the way he computes factorial, he also has to put the argument on the stack. And then when he's all done, he's going to get, you know, RA back off the stack so that you know, he can return to the right place. And you see that happening down here. Gets the argument back, gets RA back, puts the stack pointer back, right? Remember, so this is -8, right? Because that's -4 times 2, right? We're putting 2 things on the stack. Each of them takes up 4 bytes, right? 1 word, 4 bytes. And so this is -8. And if you put 3 things on the stack, it would be -12 and so on. And then when you're all done, you know, you can add 8 back to it to put the stack pointer back. Excuse me. And then he computes the result and he's all done. So again, note that in this piece of code, there's not much going on, and everything in it, even though it looks complicated, everything in it is all stuff that we've now looked at, right? You know, here's a branch, you know, a fancy branch that, you know, is made out of the SLT and BEQ. We like I said, we don't have to worry about that. You could just put in the branch. You could just put less than, and that would be fine. We don't need the 2 instruction version. And then we have the JAL, which we just learned about, which is how you know, call a routine. We have the JRRA, which is how you get back. And then we have loads and stores. We know all about loads and stores. That's how you get things from memory and put things into memory. So this is a push. This is another push. And this is a pop and a pop, you know, from a software point of view. From the processor's point of view, they're just loads and stores. And then we have a couple of adds. And that's it, right? It's our 3, you know, all we have is represented here is our 3 classes of instructions just put together in a clever way, and a subroutine call in the middle of it. I'm sorry, someone asked a question.
Yeah, Professor. Why save the, I mean, store the word the R8 on the stack. The number is 4, is not 0.
Well, so you created space for 2 of them at the same time, but you don't want to put them in the same place, right? You created 2 words of space, and so now you put one of them, you know, at 0, and the other one offset of 4, right? And the same way when you get them back, right? You just get them back from those 2 locations.
Oh, so if I create one more, then that will be 8.
That's right.
Oh, okay, I got it.
Right. So it'd be 0, 4, and 8. And then if there's 4 of them, it's going to be at 0, 4, 8, and 12, and so on. Right. You're just putting them 4 bytes apart. And, you know, and you could do it one at a time, right? You could add -4 to the stack pointer and then put 1 on, you know, just like we did before. And then you could add another -4 and put the other one on. But you see that would do the same thing. And it takes an extra instruction to do it that way. So, you know, and you don't want to, so we're amortizing, you know, we're just doing one computation to make as much space as we need. And then we're putting them in, you know, we're putting them at, you know, at successive locations, you know, in that space that we created.
So we can also switch the position, like for
yes, you can put it in any order you want. Just make sure you get it back from the same place you put it, right?
Yeah.
That would be critical. You don't put it on one way and take it off the other way. That won't work.
Okay.
Right. You'll end up with, you know, with the RA and, you know, in A0 and then A0 in the RA, and that's, you know, that program is not going to run very well. So just keep track of where you put it and get it back from the same place. Yes.
Is on the last slide.
Yeah. Sorry.
Is pushing the 2 things to the stack at the start just, you should get in the habit of doing that? Because it occurs to me that 2 lines before the L1, you're just popping them off again. And it occurs to me you could put the pushing the return address and argument onto the stack, since you're not changing them, after the branch. Couldn't you?
After which branch? The BEQ?
You could move those 2 lines to just before the add-I in the L1.
Oh, sure. Yeah. I mean, as long as you do it before you call the subroutine, right, you'll be fine. Doesn't matter where you do it, as long as you do it before you call that subroutine, before you do this. If you haven't done it before you do that, you're in deep trouble.
You're in deep weeds. Yeah.
One more question.
Yeah.
So anywhere in there, as long as you haven't called the routine.
Mm-hmm.
But you might as well do it first, right? It's not going to save you any time to put it anywhere else, you know. And again, in the old days, I tell this story several times, but in the old days, right, coders would write code to try to make it so no one else could possibly understand it, because that was job security. These days, you don't want, there's no reason to do that, right? You have infinite job security, and what you'd like to do is after you write a piece of code, you want to give it to somebody else and let them deal with it and move on to something else.
The open source movement is now a thing, and it's pretty cool.
Right. Yeah. You want to write it as neatly, as easily to understand by anybody else, and move on.
Yeah. But it does occur to me that you wouldn't have to have those two those two instructions to that one instruction to pop 2 items off the stack if you never pushed them, which you would never do if you removed those two. It would save you 3 instructions, which admittedly isn't a lot, but
No. If you don't push those guys, when you call this recursive,
I'm saying no. I'm saying you should still push them, but not do it not at the start of your function, but just after you check to see if the argument is less than 1.
Oh, I see your point. Sure. Yeah. Okay.
It would save you 3 instructions.
Yes. Fine. Yes.
And 3 instructions isn't a ton, but
dynamically, it would save you that, right? Because you don't have to go into the routine. Yes. Yes. That's true. I missed your point, and yes, that's correct.
Yeah. It's still good to be in the habit, though, of doing it at the start so you don't forget to do it.
Yeah, and of course, it's also, again, going to be easier for somebody else to read it.
That's also true.
Yeah, we don't care about any of this. So I just drew this picture. Here's a nice, pretty version of it. This is how stuff is stored in memory. And again, he uses the old word text here, which is the same as code, which is the same as instructions. All those things mean the same thing. That's where, in general, this is where programs go. Programs go here. Reserved, again, that's the operating system down there. And then you have, arrays. And then you have objects. And then the stack, which again grows down. And then again, hopefully these two things never meet. Okay. So Unicode is it's funny. We brought this up, I think, earlier, or I don't remember, but they just added, 50 more emojis to the Unicode characters or something like that. Clearly, 2 to the 32 is a big number. 2 to the 8th, however, is not so big a number, and that's this ASCII, and ASCII is what most of the text out there in the internet is stored in, because it's compact, right? We get all of the ABC, all of the alphabet, at least the English alphabet is all easily stored in those bytes. And so, again, a large fraction of the information out there stored in the internet is in ASCII. And then, of course, for all the stuff that's written in Chinese, it's all in Unicode, because the character set will not even come close to fitting in a byte. And in your program, in this next program, you're going to read in a character string, and you're going to read in a character string because we're trying to read something in the format, where all the things are on a line, right? We're going to read in a vector, 0, 3, 2, 7, 4, whatever, you know, with spaces in between the numbers. However long it's supposed to be, I don't remember. And so since we can't read this in as integers, because, you know, when you enter something into the console, to enter a number at the console, you have to enter, you know, you have to hit return after you hit the number. But we don't want it to look like that. We want it to look like a vector. And so since we want it to look like a vector, we have to read it in as characters. And since we're reading it in as characters, those are ASCII characters that we're reading in. So then you have to convert the ASCII character into an integer. And so part of the program is for you to figure out how to do that. And it's not difficult, but, you know, you actually have to think about it a little bit. And again, half of you will be using a mask operation to do it, and half of you will be doing, you know, a mathematical operation to do it. And you know, you can figure it out. It's not rocket science, but it's something, once you do it, you'll understand what's going on. So in C, there's the data type called char or car, and that's equal to 8 bits, which is what in computer land we call a byte. In computer architecture land, it's called a byte. And again, the ASCII characters are bytes. So when you read an ASCII character, you read it using not a LW, which is load word, right? You read it using LB, load byte. So if you want to read these, if you want to read out of a string of characters, if you want to read a byte out of there, you just use LB. And again, when you have bytes in memory, you're no longer incrementing by 4 to go from one byte to the next. You increment by 4 when you want to go from one word to the next. But now that we're talking about 8-bit byte things, when you want to go, if you have an array of them, when you want to go to one to the next, you now add 1, not 4. So bytes are the, you know, bytes are the natural or the natural data type of the processor from a point of view of loading and storing into memory. So the load byte is the thing that when you want to go to the next byte in an array, you just add 1 to get there, because that's what the processor computes. When it adds 1 to a number, it's incrementing to the next byte address, because that's what the processor works in. It works in byte addresses. And again, that's why you have to add 4 when you want to go from one word to the next word, because a word is 4 bytes. We won't use half word stuff at all. It's there. Half word is 16 bits, but, you know, it has really no reason for being. Okay, so here's as he says, a very, you know, dumb way of doing a string copy. And so the only interesting thing about this piece of code versus other code that we've looked at is that we now see that instead of int here, which is every piece of code we looked at so far had int as the data type, he's saying that the data type of this array is char, not int, which again is byte, means 8 bits. And again, the main thing that means is increment by 1, not by 4, as you want to go from one element of this array and this array to the next element. You increment by 1. Oh, and of course, the other thing it means is that you use load byte and store byte. And so what you see missing in this piece of code is you don't see that SLL anymore. No SLL. So we don't have to multiply our index by 4 when we index into the array. That natural index is 1 when we're doing characters. And there's nothing else interesting about this piece of code. Again, we stick S0 on the stack when we start, and we get it off when we're done because we trash S0 for no good reason other than it illustrates that if you trash a saved register, any of S0 through S7, if you trash any of those, you must save them first and then restore them. So nothing interesting going on here. Yes.
On the last slide.
Yes.
Why would you have to compute the indices every time? Why not just increment the argument registers or copy them to temporary registers?
Yeah.
And increment those instead of
yes, you can do that.
doing an add every time.
You can do that. Yep. There's several ways you can write any piece of code, almost guaranteed.
Mm-hmm. Gotcha.
Yeah. This is, if you will, the most general way of doing it. As you point out, it's not
the easiest way.
Yeah, not the fastest, simplest way.
I have a quick question for the
Yep.
last slide as well. So we're only using the store word or storing it so that after this entire code, we can get the value that was in $S0 back, right? But technically, if we don't need that value, the code will still work without using the SW and the LW.
Yeah, well, and be careful when you say we don't need that value. We has to mean the person that called this routine.
Yeah.
That's who we is, and of course that we is you. So whether you're using S0 or not. So if you came over here and used it, yeah, there is no reason for you to save it or restore it.
Okay. Thank you.
But if we're talking about general code, right, where the caller doesn't know, anything about, the callee, right, which is going to be the case for a typical library routine, right?
Yeah.
Then, you have to do it.
Gotcha.
You have to follow the convention.
Gotcha. Thank you.
Uh-huh. And again, it's recall, it's just a convention. It's what the software folks have agreed to, and so that they can write programs that work together. Okay, so we already talked about this before, that LI allows you to get a small value. A big value is gotten by stringing these two instructions together. But again, we just use the pseudo instruction LA for that, load address. So when you write LI, remember that's a pseudo instruction. It just gives you an add immediate with a constant. LA turns into these two instructions because LA means load an address. We now need a 32-bit thing. So we have to create a 32-bit thing. So when we say LA of some label, we're trying to get the address of, which is the pointer. We're trying to get the pointer to that data structure that we've allocated, and the pointer to that data structure has got to be a 32-bit thing. So we can't get 32 bits out of one instruction. We can only get 16 bits at a time. But if we get 16 bits twice, then we have a 32-bit thing, and now we have what we need. So LA, from our point of view, we just use LA. We want the address. It's very clear. We just give us the address of this data structure because we need it. Okay, we've already mentioned several times that branches are PC relative. And again, all that means is that when we go somewhere else from where we are, when we don't just increment the PC from one to the next instruction, that we're making some decision we're executing some branch instruction, that the place that we go to is relative to where we are. It's not an absolute address. It takes where we are right now, the program counter, and it adds the offset that's in the register to it. And times 4 because again, we can't, all the instructions are 32 bits, so we don't need to be able to go to any individual byte. We just need to be able to go to a word. So we take advantage of that and just make the bottom 2 bits 0. So it's confusing. It says, oh, we're multiplying it by 4. Well, really all we're doing is putting 2 zeros on the end of it, because we know that the place we're going to jump to has an even address. It's the address of a word, not the address of some individual byte within the word. And then, the rest of the branch, we already talked about. We just need these 2 things, because those are the 2 things we're going to compare. So we're going to compare those 2 things. And if we're, say, doing a branch on equal, if those 2 things are equal, then we're going to branch to program counter plus the value that's stored in here. And the value that's stored in here, again, you don't have to do anything. The assembler does all the work for you. We just want to know what's really going on. But the assembler figures out where that is relative to where you are, and it puts that value in here. So all you do is put a label. You say, branch to the loop. You're at the bottom of the loop and you say branch to the loop, branch on equal to the top of the loop, or branch on not equal to the top of the loop, depending on how you wrote the loop. And again, loop is a label at the beginning of the loop. And the assembler is going to say, okay, how far away is that? And it's going to compute that value, and it's going to stick it into the instruction for you. So what's important to take out of that is that what's here is not a 32-bit address. Well, because clearly a 32-bit address won't fit there. It's only 16 bits. What's there is an offset from where you are. The program counter is the 32-bit address. All we're going to do is we're going to add plus or minus some value to it, and that puts a constraint on how far we can branch. But it's a constraint that doesn't matter, because branches are typically relatively close by. So this is how branches work. Again, we compare the 2 values, and then we take this value and add it to the program counter. And this value might be positive or negative. If it's a loop, it's going to be negative because we're going backwards. If it's an if then else, it's going to be positive because we're going forwards. And those are the only 2 cases. So if there are occasions that you do have to jump a long way, and so there is an instruction, jump instruction, which will go a long way. And beyond that, we don't need to talk about it, because again, in the heart of a program where you're doing all the interesting stuff, you're never going to use jump, right? All your decisions are going to be made based on branches. You're never going to be jumping around. If your program is jumping all around all over the place, you'll never get it to work. Or at least you won't get it to work in an amount of time that will make you happy. So here's just an example of jump, where it's jumping to a big value. So we don't care about that. But here it has the example of branch, and you can see that it's just a tiny little value in here. And it's a tiny little value again because it's relative to this 12. We want to go from here. We want to branch from here to exit, right? And so exit is not very far away, right? It's down here at 24, it says. So when it executes this thing, it's going to start from 16 because it's already going to be at 16 by the time it adds the value to it. And then it's going to take this 2 and it's going to put 2 zeros on the end of it. So it's really, you know, instead of 1 0, which is 2, it's going to be 1 0 0 0. And so it's going to add 1 0 0 0 to 0 0 1 6. And hopefully when it's all said and done, it's going to get 0 0 2 4, because that's what we want to have happen. But the point being is that this is just a really small value because it's relative to where we are. It's not a big 32-bit address. It's relative to the program counter, and it's just adding some small amount to it based on what distance we're actually branching. Okay. And you're not going to have to do any computations like this. So you just need to understand the concept. And you can, you know, if the branch is too far away, which is just never going to happen, you can fix it. We don't care. It's never going to happen. So a summary of all this mess is here. A processor, a RISC processor is, and a CISC processor are categorized by how many of these addressing modes they have. And the more and the fancier addressing mode you have, the more you are a CISC architecture. And the less and the simplest addressing modes that you have, make you a RISC architecture. So again, MIPS, ARM, RISC-V, they all have this set of addressing modes. That's all they have. And the only important ones, this one's not important. Again, this is how you make a big jump, which not important, not the important part of any program. This one is just, you know, the one where you want a value, and you can store that value in the instruction itself. So again, this is where you're getting a small constant value. So here are the important ones. These are the three that you just want to understand. They're the fundamental ones. So this is the ALU type. Again, whenever I say ALU type, just think add. How does add work? And so again, so the addressing modes, or the addressing mode here is that you have 3 register addresses. You point at 2 operands for the sources, RS and RT. And you have a 3rd register that points at where you're going to put the result. So you're just pointing at 3 registers. So that's called register addressing. Makes sense. Completely general. For every instruction, every add, every subtract, whatever, you point it to operands, and you point at 1 result. Okay, this one is load store. For load store, you take the immediate, the offset. This is the offset into the structure, whatever the data structure is, an array or a regular, or another, you know, a standard data structure, and you add that to that register. So this is the form load word into, for instance, S0 of say 4 off of S3, right? This is our standard form. So the 4 is here. That's the offset into the structure. The base address of the structure is here. You just add those together and you put the result in RT here. And then we note that the where we put the result here, which is the nominally, that's the destination, that for this instruction type, we RD, what is really RD moves to the RT field of the instruction. And recall, this is the only real difference between MIPS and RISC-V is that they cut down the size of the offset and they leave RD here. But it's not important. And then finally, the one we just talked about, which is the branch type. And branch type just takes the program counter, PC, the program counter, and adds the offset from where we are, the relative offset, the how far away we want to go, just adds that to the program counter, and you're done. And it does that based on, you know, comparing the values RS and RT. So these are the three important addressing modes. 99% of all instructions will be one of these three types. Okay, questions about this summary?
Professor, I have a question. So is the immediate addressing for LI and then the pseudo-directed addressing for like move or LA?
Say that again. So LI is load immediate. So that's a pseudo instruction. You can use that anytime you want.
And then
and LA is load address.
It's also pseudo addressing.
That's a pseudo instruction. That converts into two instructions. Remember 2 slides ago, it shows that LA converts to 2 instructions.
Yes.
And one of them is this one, right? And one of them is this one. Immediate. Yeah. So first it loads in the top half and then it ORs in the bottom half.
Okay.
Right.
Oh, what about the move? The move also pseudo.
So this guy here, right?
Yes.
Load the high portion and then OR in the bottom portion. Right.
These two are immediate address.
Yeah, and again, for us, we just call this LA, load address.
Okay. And move is another pseudo addressing.
Move is just, you know, we saw how they do move, right? It just adds a register to 0 and then puts that in their destination. Right. So there's no move instruction. The way it does it, it just adds 0 to, you know, to the source and then puts it in the destination. Right. If you want to move A to B, then, you know, just do A plus 0 into B. Right. If you want to move B to A, just go A equals B plus 0. Right. It's clear that those are the same, right?
Yeah. So what's the difference between move and the add?
Well, there's no such thing as move.
Oh.
It just that instruction just doesn't exist. If you write move, right? A to B, right? You're going to get this. That's what, pseudo instruction means that instruction doesn't exist. That it's just a convenient way of writing it to make it easy to understand. But the assembler is going to turn it into instruction that actually exists.
Okay. So I actually changed to add.
Yep, changes it to add.
Okay. Got it. Thank you.
Mhm.
Why does load address expand into loading the bottom half and then ORing in the top half instead of a 132-bit load?
Well, because you don't have access to 32 bits, right? The biggest thing we have, let's get to it here. The biggest thing we have is this.
RISC architecture and instructions are fixed with, right?
That's right. Everything's 32 bits. You don't get anything else.
I had forgotten that.
So all we have, the only way we can make something that's 32 bits is with 216 bits. If you want to use immediate, of course, you can get it from memory. I mean, you can load a 32-bit thing from memory, right? If you've got it stored out in memory already. But that's a different way of writing the program. Okay, now, so the author here sticks the synchronization stuff in here, and he wants to make sure that we didn't gloss over it, or we didn't bypass it. And so he sticks it in right here, and it's fine because it takes an instruction to do synchronization, 1 or 2, depending on how you do it. But let's, ignoring what instructions it takes, just let's make sure we understand what it is we're doing here. What this is the world of multiprocessing. And this is multiprocessing where the two processors are working on the same problem. So when they're working on the same problem, that means they're sharing some area of memory. And so when they're sharing some area of memory and working on the same problem, because of things that we haven't talked about, but things, called cache misses, different programs, even if it's running the exact same code, are going to take different amounts of time to run. And we'll see clearly why that's true when we get to chapter 5. But right now, just accept that even if you start two programs at the same time and they're running the exact same sequence of instructions, that they won't stay synchronized. All sorts of things are going to happen. Interrupts, they're going to make them not stay synchronized. And so in order for them to share data successfully, they will have to synchronize, and put something in a lockbox and then, take it out of the lockbox. And so what we need is some atomic operation so that they can decide who can enter this, quote, critical section. They call it a critical section of code. And so what we have is in front of that critical section of code, we have this lockbox, which, and the lockbox, the way it's enforced is that, you can read the thing that's there in memory, read the thing that's in that memory location, and you can look at it and see what it is and make a decision and then write it. And you can do all that as one atomic operation. Atomic means that no other processor, while you're in there looking at it, can also go in and look at it and change it. So once you've accessed this memory location, you can look at it, make a decision, and write it. And if some other processor at the same time has come to that same point in the code, if he tries to look in it, right, and write it, he will not be able to. So his attempt to change the value will fail because you won the arbitration to set that location in memory. And again, in the MIPS architecture and all the RISC architectures, you can do this with a so-called atomic swap, or you can do it with a pair of instructions that we're going to see in a second called load word and store conditional. And here are the famous load linked and store conditional. And the beauty of load linked and store conditional is that it keeps the paradigm of it being a load store architecture. That when you go to memory, all you can do is loads or stores. If you have an atomic memory operation where you have one instruction that does both loads and stores, that breaks the load store paradigm of the RISC architecture. And so since the RISC architecture can really only do loads or stores, if you put in an instruction like this, like an atomic swap, it has to break that into 2 instructions. And so if it has to break it into 2 instructions, well, you can argue that you might as well just have put it in as 2 instructions at a time. But, this is a bit like arguing, how many angels on the head of a pin. It's you can do it either way. But anyway, so what's the important point? The important point is you have 2 processors. They want to share data, so one guy has to be able to go in and get into this critical section of code where he alters the data before the other guy reads it. And he has to be able to do that, and keep the other guy out of it while he's updating it. That's the process of computing something and then giving it to somebody else who then is going to do more computations. So parallel processing. And so this is really hard. And again, this is what many of you would end up spending a bunch of time on, is making these multiprocessor programs work. And and at the foundation of it all is the ability to synchronize these 2 programs. And again, it's done with some form of lockbox here. The details, implementation is very difficult, but the concept is quite straightforward. So hopefully, as software people, you guys, really already understand this. You have some high-level language program up here. You compile it, you assemble it, you link the stuff together. And what does that mean? That means that the things that in here where you called square root, right? These library routines where square root are located, have to get linked into your program, right? Somewhere in here, you wrote square root in your program. And when you put it all together, that square root has to be converted to an address. Where is square root? And so that's what the linker does. It's gonna replace your label has to get replaced with a real address of where square root is located. And then you just load it in the memory and away you go. Compile, link, load, and go. In old IBM, you'd see this CLLG. What does that mean? Well, it means compile, link, load, and go. Okay, so we beat to death, I think, pseudo instructions. Someone just asked about this one. There it is. We already said that any fancy branch gets converted into a 2-step process, but we don't care. We're going to use the fancy branches. You can use any one you want, greater than or equal to, whatever branch type you want. You're welcome to use it. Again, more software stuff. Here's all these symbols that have to get resolved. Again, when you wrote square root in your program, and it has to go out and find out where square root is. This is just your code. This is tells it, what this thing is. Just, this is just how you, this is so that the processor, when it sees a bunch of ones and zeros, it just knows how to interpret it. This is how the thing is put together, so it knows how to load it into memory, and then the processor knows how to execute it. It's just, this is bookkeeping. What all this is, just bookkeeping. No magic here. It's just bookkeeping. Blah, blah, blah. So here's the first time we've seen this term virtual memory. We're going to spend most of chapter 5 figuring out what virtual memory means and how to deal with it. Virtual memory and virtual to physical memory translation is the foundation of computer security. So we'll spend a lot of time on this. This is how computers are, and how we keep one user from stealing information from another user. Very, very important. Lots of magic tricks going on there. We'll talk about hypervisors and all that stuff. Anything interesting here? No. So dynamic linking is an interesting concept. It says, if your program doesn't call something in the library routine, then don't bring it in. And that makes sense. Only look through your program, and if it isn't using a particular library routine, why load that library routine into memory? So that's good. And then even beyond that, even if you've called a routine in your program, there isn't necessarily any reason to bring it in unless you actually call it. Even though it's in your program doesn't mean you ever use it. So you can, the program can wait for you to actually call the square root routine before it even loads the square root routine into memory. And these things, used to be a bit more important than they are now. We now have a lot more memory. Memory used to be a lot more expensive than it is these days. So it's it's still there and it's still done this way, but it's not nearly as critical as it used to be. And this is just a picture of doing that, right? Don't even load it in if you're not going to use it. It's boring. So this slide is important because we'll talk about Java some more. The interesting thing about Java is that Java works in two different modes, right? There's the JIT version, and then there's the interpreted version. And you can actually dynamically go back and forth between these because what this means is that Java is very, very general, right? It's this bytecode language that gets interpreted by whatever processor it's running on, but that's very, very slow. And so this is dealt with a couple of different ways. So Java is extremely important programming language. And so there's you can have a Java that's actually compiled into the native language of the processor, and that will be very fast. But sometimes they don't even do that. They'll just run it interpreted, and then they'll find where the program is spending all its time, and they'll do just in time. JIT stands for just in time. They'll do just in time compilation of just the pieces of the program that are heavily used. And so you get all the advantages still of the Java bytecode interpreted, very generality, and you get the advantages of native compiled, at the same time. And so there's an enormous amount of software out there in the world to make Java run efficiently. I mean, this problem has been beaten to death, is because Java became so pervasive, but in its standard bytecode form, it's so slow that this concept of just-in-time compilation became and is extremely important. So here it is, that same swap code that we looked at the first night, within the first half hour of the class. So it's a leaf routine. This is a sort program written in C. And this is the leaf routine that does the swap. And we've seen this code now many times. And we're just going to look at it one more time here, just for the fun of it, just because what we're going to see when we look at it is, again, what I just want you to note is that, here's a real program that does a real thing, and if you look at it, again, all it's got is these same simple operations in it that we now know and love: loads and stores and adds, and this simple shift to do a multiplication by 4. And if you go on and look at the whole thing, so here's the whole sort routine written in my favorite alphabet soup code. And then look at the real program. It's all the same stuff. You could look through here, and if you look at it at first glance, you can't tell what it's doing. But if you look over here at the individual instructions, there's nothing new. It's all just the same old thing: branches, multiply by 4, add, load word. Here's some fancy branch. Nothing new. That's my point. Nothing new. The same old handful of instructions that you see over and over in every program. Whoops, go the right way. And then here's the stuff around the outside of it. This is incredibly boring. Again, all he does is create space for 5 things on the stack, and then he puts them all on. We already had this discussion at 0, 4, 8, 12, and 16, and then when he's all done, all that other stuff fit in here. And then when he's all done, he just goes back and gets the stuff back off the stack, and then he returns. So this is a big, complicated full procedure, but it's just made out of the same 3 little things that we know how to do: adds, loads and stores, and branches. And that's it. There's nothing else there. Whoops. What in the world? Okay, so we're out of time. So when we come in on Tuesday, again, we're going to go back and do the number system stuff. So we're going to figure out this incredible magic trick that allows us to have both positive and negative numbers represented just by strings of 1s and 0s. It allows us to implement both the positive and negative sides of the number line. Just an incredible magic trick that allows us to do that. And then and then we'll, after we get through the number stuff, then we'll be done with chapter 2, and we'll move on to chapter 3, which is how to do arithmetic. First, we're going to learn what the number system is that we're going to use for arithmetic and how it works, and then we'll move on to actually, how to build the actual arithmetic operations themselves. And of course, on Tuesday, we'll have a quiz as well. And again, for any of you who've missed at the very beginning, this next programming lab is fundamental, because we're going to build on it for the rest of the labs of the class. So you really, really need to understand this next program. So that means you must sit down and write it yourself. Do not plagiarize this next program. If it even smells like you plagiarized it, you'll get a 0, and that'll be bad for your grade going forward, and it'll be bad for your understanding of the next lab, of the other labs going forward. So it's bad from your point of view and bad from my point of view. And with that, we're done.
Hi, Professor. I have a question.
Absolutely. Go ahead.
The quiz 2A, where is it stop at the chapter?
Say that one more time.
I mean, like, I would like to know how much it's gonna cover of the chapter for chapter 2 for quiz 2A.
Oh, it's basically just the first half.
Then 2 points.
Yeah, so there's two for two. Yeah, so we'll cover through writing. So the first quiz is really simple programs, and the second one is slightly more complicated programs.
Both are programs, so we have to write code for that.
Yeah. Yes, but it'll be done. You'll see how it's done. It's not completely free form, because then it would be impossible to grade it. So it's constrained free form.
So I have to finish read the whole chapter, then to do the quiz for A.
Well, or you just had to listen very carefully in the lecture. Either one. That'll always be true. You can either read the book, or you can listen to me.
I mean,
course,
do I
if you
have
do both,
to
it's even better.
finish all the slides since you haven't finished the slides?
Well, you don't have to go any further in the slides than we have gone so far for the first quiz. That's for sure.
Okay, that's what I want to know.
Yes,
Thank you.
that's for sure. Yep.
Thanks.